Welcome. Today we'll learn about Maclaurin's theorem, which helps us represent functions as power series expansions. Let's start with the general form of a power series expansion. Suppose we have a function f of x that can be written as an infinite series of terms with increasing powers of x. The key insight of Maclaurin's theorem is that we can find these coefficients using derivatives of the function evaluated at x equals 0. Let's see how this works step by step. First, let's take the derivative of our function. When we differentiate term by term, we get this expression. Let's continue and take the second derivative. Notice how the coefficients change with each derivative. And here's the third derivative. Each time we differentiate, the powers of x decrease and the coefficients change according to a pattern. Now comes the key step. When we evaluate these derivatives at x equals 0, most terms disappear because they contain x. Solving for each coefficient, we can express them in terms of the derivatives at 0. Notice the pattern with factorials appearing in the denominators. This leads us to the general form of Maclaurin's theorem. The function f of x can be written as this infinite series, where each term involves the nth derivative of f evaluated at 0, divided by n factorial times x to the nth power. We can write this more compactly using sigma notation, where the series goes from n equals 0 to infinity. This powerful theorem allows us to represent many functions as power series, which can be very useful for approximations and calculations. The more terms we include, the more accurate our approximation becomes.